Last time in phase equilibrium, we covered gamma-phi modeling. And in gamma-phi modeling, the gamma corresponds to the liquids that are modeled as real mixtures that requires a model for the activity coefficients. And the vapors are modeled as an equation with an equation of state to determine what the mixture fugacity is phi hat. Today, what we're going to talk about, and this might beg the question of if we're already using an equation of state to model the vapor, and we have an equation of state that we know models the vapor well and also works well for the liquid, why wouldn't we just use the one equation of state for both the liquid and the vapor? This gives rise to the family of models called the Phi-Phi models. So phi corresponds to using an equation of state, and in Phi-Phi modeling, we use that equation of state for both phases. So we'll start, as we always do or always should, by writing my equilibrium criterion that the mixture fugacities of a given component is equal in the vapor and liquid phases. And if I wanted to write the functionality of this, I would say that fugacity of the vapor phase is a function of temperature, pressure, and vapor phase composition, while fugacity of the liquid is a function of temperature, pressure, and liquid phase composition. And as we did last time, when we're modeling the fugacity of the vapor phase, we can do that by saying that Fi hat for the vapor phase is equal to Yi times pressure times mixture fugacity coefficient in the vapor phase. And instead of doing our regular Gibbs energy model for the liquid phase, I'm going to do the same equation for the liquid. But instead of Yi, it's going to be Xi because it is a liquid. But I can do this as well. So I can say that there is a mixture fugacity coefficient for the liquid phase as well. So when I set these two things equal, as in my equilibrium criteria tells me I should do, I know that the pressures must be equal because we have phase equilibrium. PL is equal to PV at equilibrium, and therefore my pressures will cancel. So pressure's gone, and we are left with just simply the Phi-Phi model is deceptively simple. Xi phi I hat L is equal to Yi phi I hat V. So this is the Phi-Phi model. And the crux of this model is obtaining what the mixture fugacity coefficients are for the liquid and vapor phases by using an equation of state. So how does one do that? How do you find what phi I is? Finding the fugacity coefficients. Phi i's. Well, in the last video, I already showed you how you would do this if pressure is your independent variable. So you could say ln of phi I is equal to 1 over RT times the integral from P is equal to 0 to P is equal to P of the partial molar volume V over bar I minus RT over P dP. But this one is, remember, most equations of state are written in terms of P is equal to something. So for example, in the van der Waals equation of state, I've got P is equal to RT over V minus B minus A over V square. This is the van der Waals equation of state. And here I've got pressure is the variable that is solved for. But in order to use this equation, you would need to have volume is what you'd need to find. So remember, this is a problem that we've encountered before. This was in class 9 where we talked about the fugacity of a pure component. Remember, there were two forms for that fugacity equation. And the first one actually looked a lot like this equation, and I talked about that last time, where instead of partial molar volume, it was just molar volume for the pure component. But then also remember there was that other form that had volume as the integration variable that we used when we had an equation of state where P was written as a function of T and P. So again, when P is a function of T and V, you will want to use the form of the equation with volume as the integration variable. So if P is a function of T and V, use form where molar volume is the integration variable. And what is that form? We haven't, I haven't written that one out yet. I haven't derived it yet either. I'm not going to derive this one. This is, again, the derivation that I'm going to skip. So this is an equivalent form, or ln phi I is equal to 1 over RT integral from V under bar is equal to infinity to V under bar is equal to V under bar. RT over molar volume, that's in a bracket, minus N times the partial derivative of pressure with respect to the number of moles of species I at constant T, V, and Nj, where J is not equal to I. I'm running out of room. I'm going to erase this. dV under bar minus ln of z. So either one of these are going to work. Once again, I cannot just use the van der Waals equation of state in this first form, because when I integrate this, I'm going to get an RT over, times ln of p. That's not what I want. I want to evaluate the van der Waals equation of state by plugging p into this equation and then integrating with respect to volume. There's one more issue that we have to address when we're talking about a mixture, and that is what to do about these van der Waals equations of state constants A and B. Remember, these A and B constants also pop up in Peng-Robinson and other equations of state. And what I mean by that is when I had a pure component, A and B were readily defined. But when I have a mixture, which A and B should I use? Should I use A and B for one of the components and not the other? Or what if I have a mixture that is 50-50 versus dilute in one component? How do I choose which A and B to use, or how do I assign a value to A and B? So what I mean is that when you use this equation to find what ln of phi is, this would be, you would write one of these equations for the liquid phase and one of these equations for the vapor phase. And you would have to then break up. So for example, in the van der Waals equation of state, for van der Waals, I would have to put a superscript to tell me what phase I'm talking about. So the pressure of the liquid phase would be RT over molar volume of the liquid phase minus B of the liquid phase minus A of the liquid phase over V under bar of the liquid phase square. So the question here is which component or both? And if the answer is both, how should I calculate the values of A and B? Should I take for values of A and B? And you probably have some intuition that the answer is going to be both. But if we're taking both, how do we incorporate both into this equation? Or you can probably imagine that it depends on what the composition is as well, because a mixture that is 10% component A, 90% component B will again behave different than a composition, and then a mixture that is 90% A and 10% B. Just for completeness sake, I'm going to write out the van der Waals equation of state for the vapor phase. So it's the same equation, but just with a V superscript instead of an L superscript. V square. And then further compounding the mixture, because I just said that A and B is going to be a function of composition. So the answer is going to be both, and it depends on composition. You might have wondered why I put a superscript L and V on the A and B here. And that is because remember that when we're in phase equilibrium, in general, our composition of the phases are going to be different. Depends on composition. Because it depends on composition, that means that A of the liquid phase is not going to be equal to A of the vapor phase, which is another wrinkle that we have not previously seen so far. And this is because compositions are different. And just to mention that you can do this for the Peng-Robinson equation of state, really any equation of state. We're just going to write out what the Peng-Robinson equation of state is as well. So these are the Peng-Robinson equations of state written for both the liquid and the vapor phases. You may be wondering why I didn't put the superscript on the temperature, and that is because I know that at equilibrium, temperature of the liquid has to be equal to temperature of the vapor. So therefore, I can just say it's just T. And really, you could do the same thing for P. You could say that pressure of the vapor is equal to pressure of the liquid is equal to P. But this is just written in terms of these superscripts just for clarity. We know that at phase equilibrium, the pressure of the both phases is equal. All right, so let's get on to how do we calculate what these van der Waals or Peng-Robinson coefficients A and B are. And the Dahm and Visco textbook does something that I really like, and also Sandler does something that I like as well. It differentiates. This initially seems more confusing, but it helps keep things straight. That when you have a mixture, there's a little subscript M here to denote that the coefficients are for a mixture. So I'm going to keep that as well and keep all my subscripts. Try to keep them as clear as possible, even though it seems like more work to put the M there to denote that it's from a mixture. So generally, this is a very difficult question to answer of how these A and B constants change with composition. What is normally done, this is the easiest thing to do and probably the most popular, is there's these things called mixing rules for the coefficients A and B. So calculating equation of state parameters A and B for a mixture. We'll call it AM and BM for mixtures. Even though that's a little redundant because the M, again, is a subscript that says for mixtures, but just driving the point home that it is a mixture. The A constant is typically written in terms of a mixing combination of, there's 4 terms. So there's a term for each component, so that's 2, and then there's 2 cross terms. And that's especially for a binary mixture, there's 4 terms. The more general form of this equation is sigma from I is equal to 1 to the number of components that you have. Sigma from J is equal to 1 to the number of components that you have. Yi, Yj, Aij, not alpha. And for a binary mixture, this corresponds to, if you write it all out, it's y1, y1. So in other words, y1 square times a11 plus y1, y2, a12 plus y2, y1, a21 plus y2, y2, a22. I know I said we're trying to simplify it, and this actually looks like it makes it more complicated. But remember that most of the complication is just in terms of the notation here. So A11 is equal to A1. This is the A parameter for pure component 1. Pure component 1. While A22 is equal to A2. Same thing. So this is the A parameter for pure component 2. And then the cross terms, we simplify it by setting them equal. This was maybe not the most accurate thing to do, but we say A12 is equal to A21 for simplicity. And this is another active area of research, is figuring out a better way to do this that's not too much work, and to make sure that it is generally applicable. It doesn't depend on what system it is. So we want it to be accurate for most things. Now we also say that that is equal to the square root, or the geometric mean, as this is sometimes called. So you multiply them together and then take the square root to obtain what this parameter is. So you can make all those substitutions, and you can simplify by saying, for example, that A mixture for the vapor phase is equal to y1 square times A1 plus y2 square. And remember that y2 is 1 minus y1. So I'm going to substitute that, 1 minus y1 square times a2 plus y1, 1 minus y1, square root of a1, a2. And same thing for the vapor phase, or for the liquid phase, sorry, except instead of y's, it's x's. So x1 square, a1, and I should be keeping the subscripts here maybe. A1 vapor, A2 vapor, A1 vapor, A2 vapor. A1 liquid plus 1 minus x1 square, A2 of the liquid plus x1, 1 minus x1, square root of A1 liquid, A2 liquid. Oh, wow. This is just to get the coefficients. So you can see how much work this is going to be and how much calculation it's going to be. Although with a computer, it's not so bad. So the procedure here is to find, calculating what the pure A1 and A2 is. So calculate A1 and A2 for pure components, and then plug them in to get the mixing parameters. Now, of course, remember that by Gibbs phase rule, you can set 2 of the 4 variables. So of TP, X and Y, you can only set 2 of them. And then by the Gibbs phase rule, the other 2 become set. So typically, you would either set temperature or pressure, and then X or Y when you're drawing your TXY diagram. You never set both X and Y. So in other words, when you're doing this equation, one of them is unknown. So it means it's going to be an iterative problem to solve, and for that you again use solver. Always use solver for iterative problems. Iterative problems. And I'll point out that solver is not your only option to solve this iterative problem, but I happen to think it's the most easiest, and I also happen to think that from what I hear from students who have gone on to industry, that solver is often what industry uses as well. So I want to give you some more practice of using this when you're a student. Now the rules for the B constant is exactly the same. The only difference is that for B, B12 is equal to B21, and instead of being the geometric mean, it is equal to the arithmetic mean. So B1 plus B2 over 2. This is the arithmetic mean. While the A constant was the geometric mean. So that means that it simplifies a little bit more when you're doing this equation. So when I want to write what my B constants are, Bm for the vapor phase is equal to Y1 B1 plus Y2 B2. So again, same equation up here. It just is going to simplify into this when I plug in the arithmetic mean. Same thing for Bm of the liquid phase. It's X1 B1 plus X2 B2. All right, I'm not watching my timer, but I think this is getting to be a little bit long for one video, so I'm going to stop here and come back picking up right where we left off in the next video.